Section 5.4, Calculating Changes in Entropy. We will use this equation. The exact differential of entropy is dq reversible over T. The key is to pay attention to this word, reversible. It has to be this heat flow of a reversible process. First, an ideal gas undergoes a reversible isothermal process. Well, isothermal means dT is 0. du is therefore 0 because it's an ideal gas. U only depend on T because dq plus dw is du. Therefore, dq is negative dw. dq reversible is thus negative dw reversible. Again, this is very important. When we are looking at a reversible process, P external equals P. dw is negative P external dV. Therefore, in a reversible process, dw reversible is negative P dV. We have one more negative sign here, so it's P dV. And then we can express the pressure as nRT over V for an ideal gas. This is an ideal gas. Now, delta S, that's the entropy change, is the integral of ds. ds is dq reversible over T, and we know dq reversible is nRT over V dV. We plug this in here. We get nr over V dV. We integrate this part. The result is very simple. It's nr times ln V final over V initial. What does this tell us? If temperature is constant, well, the entropy may change. The larger the volume, the higher the entropy. In an expansion process, entropy increases. In a compression process, entropy decreases. In this reversible isothermal process. What if it's reversible isochoric? Isochoric means dV is 0, therefore work is 0. In this case, dq reversible is just CV. And dq reversible is just du, it's just CV dt. Again, isochoric. Now we plug in this CV dt in this equation here. We have the final expression. It's just CV times the logarithm of the ratio of temperature. If the volume is constant, entropy depends on temperature. The higher the temperature, the higher the entropy. Again, pay attention to this expression. There's a logarithm here. This is the logarithm of the ratio of volume. Over here, this is the logarithm of the ratio of temperature. In front of the logarithm, this is nr. And over here, this is isochoric process. Therefore, you have CV in front of the logarithm of the temperature ratio. What if we have a reversible isobaric process? Well, then dq reversible is equal to Cp dt. We plug in Cp dt here. The result is going to be Cp times the logarithm of the temperature ratio. What if it's a reversible adiabatic process? Well, it's simple. dq reversible is 0. The entropy change is 0. Therefore, in a reversible adiabatic process, the entropy remains constant. Now let's look at an arbitrary reversible process. As long as it's reversible, we can use the equations, the formulas obtained from A, B, C, and D. And then let's say the initial state is Pi, Vi, Ti. The final state is Pf, Vf, Tf. We just need to design a two-step process. In the first step, the volume is held constant. We just change the temperature from Ti to T final. Of course, P, the pressure is going to change, but we don't really care about the pressure change. Just focus on this isochoric process. In isochoric process, we've got the formula here. The entropy change is Cv times the logarithm of the temperature ratio. Second step, we hold the temperature constant. Okay? And then this time, the volume is changed. When temperature is constant, we use the reversible isothermal process over here, the temperature change is 0. Therefore, du is 0, dq plus dw is 0, dq reversible is negative dw. We go through all this derivation, we get the entropy change to be nr times the logarithm of the ratio of volume. So we just put it in here, the ratio of volume, logarithm, and nr Cv times the logarithm of temperature ratio. So again, in this step 1, this is the entropy change. In this step 2, as a isothermal process, this is the entropy change. And then we just sum it up, we get the total entropy change from the initial state to the final state. Okay, this is a reversible process. Now, what if I give you an irreversible process from this initial state to the final state? How do you calculate the entropy change? Here's the hint. Entropy is a state function. So if you go from here to here via a reversible process, and then if you go from here to here via a irreversible process, how does that change the value of delta S? There's no change, same thing. So actually, for an arbitrary irreversible process from the initial state to this final state, the change in entropy is still the sum of these two terms. No change at all. So it may seem confusing, but look, I'm going to ask you another question. Let's say in an arbitrary reversible process, the state of the system changes from this initial to the final state. How do we compute the change in pressure? Well, you'll say it's Pf minus Pi. Now I'm going to change the question to an irreversible process from this state to this state. What's the change in pressure? Well, it's still Pf minus Pi. Well, pressure is a state function, right? So the change of pressure is simply the final pressure minus initial pressure, regardless the reversibility of the process. Same for entropy. The state, the system changes from the initial state to the final state. And therefore, if the process is an irreversible process, you simply design or imagine a different reversible process like this one. Do the calculation, get the result, and this result is the entropy change of the reversible process, but also it's the entropy change of the irreversible process. So this is what this F is about, how to calculate the entropy change that undergoes an irreversible process. Same expression. As long as we have this initial state, this final state, same expression. Now let's prove this for a reversible adiabatic process of an ideal gas. You saw this in the chapter on the ideal gas. Now we can prove it in just a few steps. So first, the entropy change should be 0 because it's a reversible process. And 2, we go from the initial state to the final state. So we can just copy this expression in here. All right? So this is the entropy change from the initial state, Pi, Vi, Fi, to Pf, Vf, Tf. All right? And we now know this sum is 0. And then algebra here, Nr is Cp minus Cv for an ideal gas. Again, for an ideal gas, Cp minus Cv is Nr. And then what we do is we move things around. And remember, Cp over Cv is simply gamma. Now it's easy to see the logarithm of the temperature ratio is 1 minus gamma times the logarithm of the volume ratio. In the end, the ratio of temperature is equal to the ratio of volume to the power of 1 minus gamma for the reversible adiabatic process of an ideal gas. Finally, let's revisit the Carnot cycle from a different perspective. Remember, when we look at the Carnot cycle, we used a PV diagram. This time, let's use TS diagram. The reason is very simple. The integral of PDV is work. The integral of TdS is heat in this reversible process. Now, this time, this rectangle area is the amount of heat that's converted to work. Because in the isothermal expansion, the area below this AB line, so this rectangle, this large rectangle, is Q hot. And then when it's doing C to D isothermal compression, this part is Q cold. Okay, so what's the difference? The difference is this rectangle. That's the amount of heat being converted to work. What about the adiabatic expansion, adiabatic compression? Well, there's no change in entropy, therefore the integral of TdS is 0. All right, so there's no Q involved here or here. Again, this is Q hot. This small rectangle is Q cold. The difference between the absolute value of Q hot over this one and the absolute value of Q cold is this rectangle, and this is the amount of heat that's converted to work. And in general, let's look at entropy again. It depends on temperature and volume. Does it depend on pressure? Yes, it does. But again, pressure depends on temperature and volume. It's a dependent variable in this case. Can we say temperature depends on temperature and pressure? Yes, of course. But whatever is convenient for you, you are free to choose 2 out of the 3 variables PVT, and then determine how entropy depends on either TV or TP. In this case, let's say entropy depends on TV. So let's derive this equation for dq reversible. It's du minus dw, reversible. And over here, this guy is negative PDV. And du can be expanded as delta u over delta t times dt, plus delta u over delta v times dv. Minus negative PDV is plus PDV. Now this one is internal pressure. The internal pressure can be expanded into T delta P over delta T minus P. We can prove this after chapter 6. Now this negative PDV and positive PDV cancel. We have the result here. dq reversible is CVDT plus P times delta P over delta T times dV. Now we plug this expression into this formula for entropy change. Okay, we plug it in. We have this integral of CVDT over T, and also we have this PDV over T. Well, this is for ideal gases. I forgot to mention that for ideal gases, delta P over delta T is simply nR over V. And then nR over V times T is just pressure, so over here. All right, so the entropy change for the ideal gas is this guy, and then we can simplify it. We get the same expression, Cv times the logarithm of the ratio of temperature plus nR times the logarithm of the ratio of volume. Now we're going to use this expression for van der Waals gas. The VDW equation is this, so delta P over delta T is actually nR over V minus NB. Now we have dq reversible as this formula. Look, the volume for the ideal gas is replaced with V minus NB for the van der Waals gas. So that's the difference. Now we plug in this expression. This is dq reversible to here, and then divided by T, and then we integrate everything. We get Cv times the logarithm of the ratio of temperature plus nR times the logarithm. Now, this is the corrected ratio of volume. So we have the volume of the container minus the size of the molecules. For solids and liquids, we use the same expression for dq reversible. Okay, it's here. But for solids and liquids, we learned that delta P over delta T is simply beta over kappa. We do this conversion because beta and kappa are roughly constant for solids and liquids. It's just easier to express delta P over delta T as beta over kappa. And then we integrate this dq reversible over T. So again, we have CV times the logarithm of TF over T initial over here. But what about the second term? The second term is the integral of this guy over T. So T and T cancel. We'll just need to integrate this part. Now, for liquids and solids, the entropy change does depend on the volume change. But the expression is a little different. It's beta over kappa times the volume change. Remember, we said the entropy can depend on temperature and pressure as well. In this case, volume depends on temperature and pressure. All right? So we derive this dq reversible again. This time, it's du minus dw reversible, and we replace du with dh minus pv. Okay, h minus pv is u. Now we expand this dh over here. This is dh. Cp is delta h over delta t. Okay, and then minus pv. All right, over here. The exact differential of dpv is pdv plus vdp. Now with the negative sign in front. How about negative dw reversible? It's just negative pdv. So therefore, it's positive pdv. pdv and pdv cancel. Then we expand this part. This part is equal to v minus t times delta v over delta t. The derivation from here to here can be done after you learn chapter 6. For now, let's just accept this expression. And v, dp, and negative v dp cancel. So we have dq reversible as a function of dt and dp. Again, we plug this into the formula of entropy. For ideal gases, or C, dq reversible is simply Cp dt minus vdp. And then we have delta S is the integral of ds. The integral of ds is the integral of dq reversible over T. And then we have this formula. The formula is Cp times the logarithm of the temperature ratio minus Nr times the logarithm of pressure ratio. The reason is when we integrate this part over T, it's negative integral of V over T dP. All right, and V over T is actually Nr over P. So we're integrating negative Nr dP over P. So that's going to be logarithm of PF over P initial. For a van der Waals gas, this equation holds approximately. So I put a approximate equal sign here. For liquids and solids, again, we'll use this expression and plug it into the integral of ds reversible over T. So the result is simple. Again, it's Cp times the logarithm of Tf over T initial. But how do we integrate this part? Well, if you recall the definition of beta, beta is isobaric thermal expansion coefficient. So beta is 1 over V times this derivative. Therefore, this derivative is simply V times beta. We plug it in. Beta is roughly a constant for liquids and solids. And then we have the final expression for the entropy change of liquids and solids. It's Cp times logarithm of the ratio of temperature minus the volume of liquids or solids times beta times the change of pressure. For phase transitions such as fusion, it's very easy. Delta S, again, is the integral of dq reversible over the temperature. In this case, let's assume this fusion is under constant pressure. And this part is constant pressure process. Diffusion is the melting point under constant pressure. So this is a constant actually. We take it out, we integrate dq, it's just q. And when we look at this, constant pressure tells us q is delta H. So the result is simple. The entropy change in a fusion process is simply delta H fusion over T fusion. This equation, you learn this in general chemistry. What about vaporization, sublimation, some other phase changes, phase transitions? The same. The entropy change in a phase transition. It can be fusion, vaporization, or sublimation. It's just delta H of the phase transition divided by the temperature of the phase transition. That's how you compute the entropy change of a phase transition.